Hi, this is a demonstration of the Connect Chapter 6 homework number 3, where a hot steel ball bearing is dropped into a beaker of water. So you're given temperatures of the water in the steel ball before this heat transfer happens, as well as their masses, and you're also given a specific heat. These should be clues that you'll want to use an equation for heat transfer. And your equation for heat transfer, first of all, there's the kind of big picture that any heat that is lost by the steel ball is going to be absorbed by the water. And so this is an application of the conservation of energy. If heat is lost by one thing, it's gained by another thing. So we can start off with that equation. Now all we have to do is substitute in the expression for heat transfer. That heat transfer is equal to mass times specific heat times your change in temperature. And the same goes for the water. Mass times specific heat times change in temperature. So that's going to be the most important formula for this chapter, but let's think about what's really happening. We've got a vessel with water in it, and we've dropped in a steel ball bearing. And let's just kind of summarize all of the things we know about these two systems. The mass of the steel ball bearing is 41.55 grams. In this version of the problem, you might have slightly different numbers. The initial temperature, Ti, is 104.89 degrees Celsius. Then the water itself has a mass of 116.9 grams, and the temperature, the initial temperature of the water, is room temperature, 22.47 degrees Celsius. Now what we need is an expression for delta T, because the change in temperature is what the heat transfer expression calls for. So delta T we're going to define as the change in temperature between final temperature and initial temperature. And the thing is, once the system equilibrates, the final temperature of both the ball and the water will be the same. So we're going to call that final temperature X, and the change in temperature is simply the final temperature minus the initial temperature. So you can see that, this one thing to note is that final temperature is going to have to be somewhere in between the temperature of the steel ball and the temperature of the water. So the delta T for the steel ball will be negative, because say that number ends up being 30 or 40 or 50. That'll be a negative number, and this one will end up being a positive number. One other thing we know about these two materials are their specific heats. Let me just draw a line to separate these guys here. Top information is for the steel ball. Specific heat for the steel ball is given to us, 0.474 joules per gram degree C. Specific heat for water is 4.18 joules per gram degree C, and you've seen that number a few times now. Okay, and so just to complete my notes here, the final temperature, what we're looking for is X. That's where that X comes from, and that's where that X comes from. And that final temperature will be the same for both the water and the steel ball. All right, so let's start plugging in here. Really, this problem just kind of ends up being a lot of algebra, because we have 3 variables in each side of this equation, but we can fill in for all of them, and then our delta T's both have X's in them, so we'll end up solving for that X. So the steel ball, M is that 31.15. I wrote 41.15 here, that's wrong. That should be a 3. I have a slightly different version of this problem loaded up here, but the methods are the same. So 31.15 grams times our heat capacity, which is the 0.474 joules per gram degrees Celsius, and that's going to be equal or times the change in temperature, which is X minus 104.89. Well, that's a 4 right there. And that's equal to the heat absorbed by the water, which we just use that same expression for heat transfer. Mass of water times specific heat of water, 4.18 joules per gram degrees C, times our change in temperature, which is that expression involving X for the final temperature minus the initial temperature. All right, now, there's just a lot of algebra here. We want to multiply these two together and then distribute it over the parentheses. So we'll end up with this times X, and then that times that, all multiplied together, added or subtracted depending on the sign. So yeah, we should end up with minus 14.77x, and I'm going to skip the units here. We'll come back to them later. Plus 1,549 on the left side of the equation. And then if I multiply that times x, I end up with 488.6x minus 11,537. So now I just need to combine like terms. I need to combine my x's. So if I add this guy or subtract this guy over here, I end up with 503.4x, and that's going to have a negative sign on it. So minus 14 minus 488, and that's going to be equal to minus 13,085, oops, that's an 8 right there, 85.8. And then dividing these out, I end up with x equals 26.00. So, nice even number right there. And what did I define my x as before, remember? I defined it as the final temperature. The change in temperature was the final minus the initial. Change in temperature is the final minus the initial. So this is the final temperature of both the ball bearing and the water. Now, quick check, does this make sense? You might have expected the final temperature to be somewhere closer to the middle or the median between the initial temperature of the ball, 104 degrees, and the water, 22 degrees. But essentially what this is showing is that water has a very high specific heat. It takes a lot of energy to heat up water. And the ball bearing is just a small ball that was dropped into a much larger mass of water. So it makes sense that the temperature doesn't actually rise all that much.